Today I'm going to be talking a little bit about cesium carbonate and organic reactions, but before we start, I'm Collin Sylvain, I'm 18, I'm a senior at Hampshire High School, and this is my 5th year doing science fair. A couple of acknowledgements. Thanks, Mom, for everything you do and everything you put up with. Also my science teachers for helping me along the way, my sponsor this year, Mrs. Ibarra, and Mr. Lindley for helping me through this entire process. So the purpose of this experiment is to explore the efficacy of organic reactions such as, or in this case, epimerization, when performed with different inorganic bases that all have differing alkali metals, in order to discover which one of those inorganic bases makes the most effective compound. Or to sum it up, we're going to look at which inorganic base or which compound makes this reaction work the best. So my hypothesis for this experiment is that if we use cesium carbonate as the agent in a pool of cesium carbonate, potassium carbonate, and sodium carbonate in this epimerization reaction, then the yield of the wanted isomer, or the chemical that we want from the reaction, will be higher because of the individual size of the alkali cations, or the size and the makeup of cesium compared to potassium and compared to sodium. The first step in materials and procedure is gathering the materials to complete the epimerization reaction and gather materials to complete thin layer chromatography, which will help us compare the results of the epimerization reaction. So we need to gather our inorganic bases. As I said previously, cesium carbonate, 15 grams, potassium carbonate, 15 grams, and sodium carbonate, 15 grams. Each one of those is necessary to complete one epimerization reaction. Then also in this epimerization reaction, one run is going to require 200 milliliters of toluene, as well as the substance we are epimerizing, which is catnip essential oil. For the epimerization reaction, we also need the correct glassware and equipment, such as a heating mantle, a 500 milliliter round bottom flask, a condenser in order to catch the toluene, as well as other appropriate glassware. Then, to complete thin layer chromatography, we need the solvent, which in this case was a 95% to 5% petroleum ether to ethyl acetate solvent, as well as the thin layer chromatography sheets themselves, as well as microcapillary pipettes. Then the epimerization procedure proceeds as adding the chemicals to the round bottom flask, bringing it up to a boil, and leaving it for 25 minutes. Once the toluene is evaporated off, you can then use the constants in thin layer chromatography. And just a little side note, there's usually a large percentage error that happens with any organic chemistry related project or reaction, so keep that in mind. Your results may vary depending on when you're doing this or how you're doing this, because it can be pretty finicky. I was lucky enough to have the cesium carbonate trial and the potassium carbonate trial go very smoothly on my first try. However, the sodium carbonate trial I did 3 times and I still could not get the intended effect that I wanted. In this experiment, the thing we're changing throughout is the inorganic base, so whether that be cesium carbonate, potassium carbonate, or sodium carbonate. Then the dependent variable is the way the TLC plate looks when it comes out and how much ZE isomer is epimerated, or how well the reaction goes. The controlled variables are some constants. The temperature of the water was always brought up to a boil and nothing hotter. The amount of toluene, 200 milliliters, and the amount of catnip oil, which was 5 milliliters, were kept constant. Then the length of the epimerization reaction was kept constant as 25 minutes. The control group is the TLC plate that is spotted with pure catnip oil. And the experimental groups are the TLC plates that are spotted with the epimerization reaction of the inorganic bases. In these results, we see thin layer chromatography sheets. The way chromatography works is by separating a substance by polarity. The more polar a molecule is, the less it will travel up the solvent, or the paper. So in this case, the EZ isomer, or the one that's always on top, is less polar than the ZE isomers. So looking at the control group, the TLC spot with pure catnip oil, we can see that the majority of the sample has EZ isomers, which is why we're doing an epimerization reaction to try to convert the EZ isomers to ZE isomers, which is what the inorganic base helps with. So as you can see with cesium carbonate, the EZ and ZE isomers start to even out, and there's more ZE isomers than EZ isomers. There's a really concentrated secondary dot right above where the sample was spotted, which shows the abundance of Ze isomers over Ez isomers. In potassium carbonate, you can see there's still quite a few Ez isomers, which is what we started with, but there still is some Ze isomers there. Then the TLC spot with sodium carbonate failed all 3 times I tried to do it, which might be a case for how small the sodium cation is, but that is something definitely to look at. So overall, my hypothesis was generally proven correct in a qualitative sense. These TLC samples are only qualitative. To be more precise, we'd have to go into different routes using nuclear magnetic resonance to be able to tell the exact makeup of a certain molecule. But based on qualitative TLC samples, it seems there is the most abundance of Ze isomers, which is what we were going for in the conversion to Ez to Ze isomers. The quality of the results also proves the notion that larger cations produce a better conversion results, since the size of the alkali metal's atom radius is in the same order as the yield results: cesium-1, potassium-2, and sodium-3. This can also prove really useful in the real world, both in actual application and in education. Right now in colleges, organic chemistry textbooks don't use cesium carbonate in workbooks, even though it's proved by multiple studies to be more effective than other inorganic bases. So by showing that cesium carbonate repeatedly is more effective than other inorganic bases can help future students apply this more often. This understanding of the efficacy of cesium carbonate can also be useful in manufacturing sense, and it can help overall yields and efficiency of certain manufacturing processing, which can earn more revenue or be more efficient overall for a company. Alright, thanks for watching.